So, learning goals in this particular chapter, some of them will be um, some things that you will recall from general chemistry, but this is where we really start talking about organic molecules, so to speak, and we're going to learn about their properties and what contributes to their properties and those types of things, what a functional group is. So we're going to start off by talking about hydrocarbons. Now that name means what? What does the name hydrocarbon mean? Pardon? They are completely made up of carbon and hydrogen. A pure hydrocarbon will be a molecule that only contains the atoms or the elements of carbon and hydrogen. That is correct. And there are several different types of hydrocarbons that we'll learn about. We're going to talk about polarity. We're going to talk about what causes polarity. Okay? When you hear the word polar, what do you think? Okay, one end's positive, one end's negative. And how does that result? Unequal electronegativities will certainly come into play, right? And if we have unequal electronegativities, we have permanent dipoles, but we can also have situations where we have temporary dipoles, okay? And so we'll talk about those types of things as we go along this semester as well, okay? And then, of course, a functional group. And so what is a functional group and how do we identify them? Those are some things we're going to learn in this chapter. What does the term functional group mean to you all at this point? Pardon?
We learned about it.
You did? Okay, so it's either an atom or a group of atoms that have a special function. Okay, and it doesn't really matter whether or not you put that functional group in a small molecule or a large biomolecule. Its reactivity is about the same. They will differ. Okay? But for example, aldehydes and alcohols, if you put them in a small molecule, they have similar reactivity than if you place them in a large molecule. They have a particular function, okay? And we'll talk about those, okay? So let's start off with hydrocarbons. Again, we've already established that these are molecules that only contain carbon and hydrogen. What's the electronegativity difference between carbon and hydrogen? Large or small? It's really small, right? There is an electronegativity difference, but it's pretty small. And so would we expect that these molecules would have huge dipole moments? Would they be highly polar or would they be more nonpolar? They're very nonpolar, right? And so would we expect them to be soluble in water or not? Not, right? Because water is very polar and hydrocarbons are very nonpolar, right? So some common examples are methane, CH4, and ethane, C2H6. These are saturated hydrocarbons because we have the maximum number of hydrogens that those carbon atoms can actually hold on to, so to speak, in these molecules. Okay? We also have examples like ethene and ethyne. Notice here, compared to ethane, what do we notice in terms of their formula? Less hydrogen, right? They have less hydrogens. How many less hydrogens do we have for ethene than for ethane? 2. And how many for ethyne versus ethane? 4, right? So these are unsaturated hydrocarbons because they actually contain fewer hydrogen atoms than the number of carbons would theoretically allow, okay? And so these molecules will have what kind of bonds? They will have a double in ethene and a triple in ethyne, and those double and triple bonds are also known as what kind of bonds? They are known as pi bonds. Are pi bonds weak or strong? Are they? The pi bond itself is actually weaker than a sigma bond, and we're going to learn about that this semester. Now, you're absolutely right that a double bond, if I take into account the single bond or the sigma bond and the pi bond together, that's stronger as a unit. But the pi bond itself is actually fairly weak. Okay? We're also going to learn about aromatic hydrocarbons. When I say the word aromatic, what comes to your mind right now? Smell. That's exactly right. To a chemist, aromatic means something different. Many aromatic compounds do have an odor, but that's not what we're talking about. We're not talking about perfumes here, okay? So aromatic compounds are another class of hydrocarbons that have very special properties, okay? They're more stable than you would expect based on just their structure alone, okay? And so we'll learn more about that later on in another chapter. So let's look at methane, the simplest of the hydrocarbons. Okay, it is the main component of natural gas. It can be anywhere from, actually it could probably be higher than 80%, but on average, natural gas is somewhere between 60 and 80%. Methane, you also have some ethane, some propane, some butane, and other things like that in natural gas. It's found largely in geological deposits, right? We have natural gas wells. Usually wherever you see a lot of oil drilling, there's also, they call it oil and gas exploration because natural gas typically exists where you have large oil deposits. We have an entire industry, especially here in the South, that is based largely on these fossil fuels, right? If you've ever gone off the coast a little ways, you see all these little things in the ocean, right, in the Gulf that are producing natural gas and oil, okay? Mainly these things are used to provide us the fuel that we use, right? If you drove to school today, chances are you had fossil fuel in your tank that got you here, right? Unless you're driving like something like a Leaf or something like that, right? But for the most part, we use fuel that comes from these natural deposits, okay? In the United States, natural gas is one of the primary energy sources used to power power plants and produce electricity. The next biggest competitor to it is coal. Why would a electric company prefer natural gas over coal? What do you mean by that? Okay, so they do call it a cleaner fuel. It does not produce ash. It does not produce soot, right? Does anybody know what the big problem with burning coal is? It has to do with the fish that you eat. Can anybody tell me what it is? It's not lead, but it is a heavy metal. Mercury, that's right. So it turns out that coal contains a small amount of sulfur. And sulfur is also known as a mercaptan, which means it grabs onto mercury. So even though there's very little mercury in a lump of coal, how many tons of it do we burn on a daily basis? Lots of tons of it. And that mercury gets emitted into the atmosphere. It ends up being deposited into the Earth's oceans by rain. Little fish accumulate that, and then what happens to the little fish? They get eaten by the big fish, and what do we do with the big fish? We eat the big fish, right? And so you have to worry about mercury contamination in the oceans because of it. And so electric companies have started trying to produce more and more of their electricity from non-coal related sources because of it. Okay? Methane is produced by a bacteria called a methanogen, and so under oxygen-free conditions, these microorganisms actually will convert organic material into methane. And these things are found in the oceans, they're found in mud, that stench from sewage contains some methane, and even in the stomach of cows, they have methanogens, okay? So cows actually contribute to a huge amount of natural gas, methane emissions, and methane is actually believed to be a substantial greenhouse gas, right? And so methane emissions are somewhat problematic. There are huge deposits of methane that have been trapped deep in the ocean as hydrates. And these, if you've ever seen them on, like you can look at YouTube, they've got pictures of these things. They're beautiful crystals. And it looks like little ice forests down in the ocean. But this methane has been trapped in these ice crystals, and they're called hydrates. And we believe that there's enough hydrates in the deep ocean to actually give us all the natural gas that we would need for the foreseeable future. The problem is, how do you go that deep in the ocean and bring those things up and use it on an economic scale? And we just haven't figured that part out yet. But there are huge, huge deposits of these methane hydrates all across the globe deep in the ocean. Okay? We know that methane, CH4, is actually tetrahedrally shaped, almost a perfect tetrahedron. It has bond angles of 109.5. The bonds are all single bonds. All 4 hydrogens are said to be equivalent. What do we mean by that? I'm sorry, I couldn't hear you.
The equal distance from the carbon and other hydrogens.
Okay, that's true. What else could it mean? So if I asked Amber to close her eyes and I went up there and I turned the picture, could she tell that I have done that once she opened her eyes? No, because no matter how I turn it, it looks the same, right? So all of those hydrogens are actually identical. She wouldn't be able to tell that I actually turned the picture at all. Okay? Alkanes are known as aliphatic hydrocarbons, and they only contain sigma bonds, carbon-carbon sigma bonds and carbon-hydrogen sigma bonds. Okay? Acyclic alkanes, that is, alkanes that aren't part of a ring, okay, will have a molecular formula of CnH2n plus 2. If a molecule satisfies that equation, we say that that alkane is saturated. Okay? N has to be an integer. You have to have a given number of carbons. You can't have half a carbon, right? So if we had 3 carbons, how many hydrogens would we have? That's right. You would have 8. And so that makes sense, right? Because if we look at the structure of propane, for example, we see that we can get 8 hydrogens around it. So each one of the carbons is certainly going to be a CH2, and then you've got to have 2 hydrogens on the end to take care of the remaining valences, right? Now, we can have things that look like that, right? C7H16. That is what we would call an acyclic alkane, okay? It's also known as a linear alkane, but is it really linear? Why do we call it a linear alkane or a straight chain alkane? Well, there are no functional groups off of it, that's true, but that doesn't have to do with the shape. Straight line? Is it a straight line? For the most part. Well, it's definitely not cyclic, that's true. But I'm zigzagging, right? Because those are all tetrahedra. But where does it get the name linear alkane? Because if we write it out, right, in condensed form, we would write it out in a linear fashion. That's where it gets the name. But it does have a zigzag shape to it. It's not truly linear, right? Cycloalkanes, these are going to be alkanes that are only carbon and hydrogen, obviously, and they're part of a ring or rings, okay? So for example, cyclooctane, 8 carbons. What can you tell me about the formula there? Is that saturated or unsaturated? It is unsaturated. By how many units of unsaturation? 2 hydrogens, but 2 hydrogens is considered a single unit of unsaturation. So it is unsaturated by 1 unit of unsaturation, okay? And so why does it have to be unsaturated if it's cyclic?
Because there's no clean carbons.
Yeah, so the...
Have 2 bonds to carbon.
Yeah, so if we had the 8 carbons, right, and we had it saturated, we would have these 2 additional hydrogens on the end. And to make the ring, we would have to remove those 2 hydrogens to bring those 2 carbons together, right? And so that's a unit of unsaturation. So unsaturations, based on what we've learned right now, can be rings or what? Double bonds or triple bonds. That's right. So a unit of unsaturation can come from a ring, A unit of unsaturation can come from a pi bond, okay? So there are many ways to have unsaturation, okay? You need to know the names of these things to about, 10, okay? You need to know methane is 1 carbon, ethane is 2, propane is 3, bute is 4, pent is 5, hex is 6, hept is 7, so on and so forth. You need to know those. You need to know those alkanes by name, okay? So if I come into class on Monday and I say, draw the structure for pentane, you'd be able to draw pentane and you would know that that has 5 carbons and 12 hydrogens, okay? Now, anybody would tell you that 20 carbons is not a large molecule. For those of you in polymer science, you deal with molecules that have millions of carbons, right? Huge polymers. So 20 carbons is nothing, okay? And 20 we would call icosane. But notice what's happening to the number of constitutional isomers. What do I mean by constitutional isomer? I'm sorry? Same molecular formula, but a different structure, right? That works good enough for right now. So methane can only be CH4, 1 carbon, 4 hydrogens bound to it. If I take a hydrogen off and move it over to where another hydrogen was, it's the same thing. I haven't done anything, right? And that's the same case for ethane. I can only have 1 structure of ethane and only 1 structure of propane. But once I get to butane, I can start to move things around and get different structures. Notice with 4 carbons, I have 2 constitutional isomers. With pentane, I have 3 constitutional isomers. Hexane, I have 5. Heptane, I have 9. Octane, I have 18. Nonane, I have 35, right? Just by adding an additional carbon and 2 additional hydrogens, I go from 18 to 35 constitutional isomers. Now, when I have 20 carbons and 42 hydrogens, I have 366,319 possible different combinations that are unique structures. And I just told you that 20 carbons is nothing, right? So this should illustrate to you the power of organic chemistry to give us multiple structures. That's why we're organic based, because we can have multiple structures with very few numbers of carbons. That's one of the magic things about carbon. We don't find that with oxygen. We don't find that with nitrogen. We definitely don't find that with any of the halogens. Okay? We find this type of structural diversity in the chemistry of carbon. That's why carbon is the basis of life. It's the basis of biology. It's the basis of biochemistry. Okay? It is what allows life to exist, is because carbon sits right where it sits on the periodic table, and it can form all these chains, and it has a valence of 4, and the sigma bonds are pretty strong, and it can have weaker pi bonds that allow for reactivity, and you can hook other things onto it that give it different function. All that together is why we have organic at the center of life, really. In fact, organic, right? If you'll recall back from day 1, right? People used to think that organic had to come from life, right? That was the vitalism theory, right? And so you can understand why they believed that at the time, because they were finding these molecules from living things, right? Makes some sense. So what am I going to hold you responsible for in terms of giving me the number of constitutional isomers? Well, I'm definitely going to exclude icosane, right? Probably not going to have time on an exam to do anything like octane, but I would say somewhere around hexane, right? You ought to be able to draw those structural constitutional isomers. Okay, you should be able to do that. But I'm certainly not going to give you something where it's going to take you the entire 50 minutes to just draw some constitutional isomers. Okay? And definitely not 366,319 of them. Okay? All of the carbon and all of the hydrogen that you have in an alkane is not equivalent. There are different types of carbon. Okay? So we can have primary carbons Okay, notice that it's abbreviated as a 1 with a degree symbol. Okay. A primary carbon is any carbon that is bound only to one other carbon. A secondary carbon is bound to how many carbons? A tertiary carbon and a quaternary carbon. 4. Those carbons have different reactivity. A primary carbon reacts differently than a secondary carbon, than a tertiary carbon, than a quaternary carbon. Okay? What's happening to the number of hydrogens that we can have on a primary carbon? How many can I have on a primary carbon? 3. So methyl groups, CH3 groups, are very good examples of primary carbons. Secondary carbons, how many hydrogens could I have? Tertiary and quaternary, 0, right? And if we look at this particular example, we can see the different types of carbon atoms within a single molecule, right? Here we have a primary carbon. Is that the only primary carbon in that molecule? No. All of the CH3s are primary carbons, right? Notice I've got a secondary carbon, I've got a tertiary carbon, and I've got a quaternary carbon. Okay? You will need to be able to identify by sight the different types of carbon within an organic molecule. And this will become extremely important when we get to start talking about reactions. So when we start talking about substitution reactions work really well on primary carbons, but they stink at tertiary carbons. And if you can't identify the different types of carbon, that's going to cause you a problem. Okay, so you need to be able to identify the different types of carbon within an organic molecule in a fairly quick and straightforward manner. So let's do a quick concepts test. Get out a sheet of paper and identify the primary, secondary, tertiary, and quaternary carbon atoms in this molecule. So the first thing you need to do is draw that molecule and then identify the types of carbon. How many primary carbons do we see up there? 6? Where are they? Okay, so here, 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 and here, right? So that's 6. How many secondaries do we have? 2. Tertiaries? 2. And quaternaries? 1. Right? Very important skill, but seems like you all got it. Let's see. 1, 2, 3, 4. It's a heptane molecule. We'll learn about naming it later, but it is a derivative of heptane. Never counted the carbons in it before, I just made it up. So. Alkenes are another form of hydrocarbon. These are unsaturated, right? These things have pi bonds. The two simplest that we know of are ethene, C2H4, and propene, C3H6. These are industrially important, okay? So if you take ethene, you can get polyethylene What is polyethylene useful for? Or what is polyethylene? Let's start with that. What is it? It can be used to make water bottles, but it's plastic, right? This is probably one of the more common plastics that people come into contact with, right? You go home, you get your milk jug, you look at the bottom, you'll see a little recycle symbol, and it'll say HDPE, high-density polyethylene. There's also low-density polyethylene. There's other types of polyethylene, but polyethylene is one of the more common plastic materials that we come into contact with. When these slides were made, and these slides are old now, but at the time that these slides were made, 30 billion pounds per year of polyethylene were made in the United States. That's a lot, right? That's a lot of milk jugs and water bottles and plastic sheeting and whatever else that we make out of it. Gasoline tanks these days are made out of high-density polyethylene because they don't rupture in a car accident, right? They hold on to their fuel contents pretty well. Propene can be polymerized to make polypropylene or polypropene, about 15 billion pounds per year in the United States. Polypropylene, if I'm not mistaken, is one of the primary constituents of artificial turf. So if you ever play on a field with artificial turf for soccer or football or whatever the case may be, it's mostly polypropylene, okay? 15 billion pounds per year in the United States at the time of these slides. That's a lot of stuff, right? Alkynes, these are going to be things like ethine or acetylene, excuse me. Where do you all know about acetylene? Torches, that's right. Oxyacetylene torches. This is how you cut through steel, right? Or how you can weld and braze and those types of things if you've ever done that kind of stuff. It's an industrially important material, okay? It is the oxyacetylene torch fuel, okay? It gets real hot when we burn it, okay? It's the simplest alkyne. How many pi bonds does it have? It's got 2. So the carbon is bound to the other carbon by a sigma bond and 2 pi bonds. And those pi bonds are oriented how with respect to each other? What's their angle between them? Well, 180 is the bond angle for the 2 carbons and the hydrogens, right? Those are all 180 degrees. But I'm talking about, I've got a pi bond and then I've got a second pi bond. How are they with respect to each other? Are they like this? Or are they like this? That's orthogonal. They are orthogonal to one another. They're at 90 degrees. Remember that the pi bonds are made up of p orbitals, right? And so you have px, py, and pz, and all those are 90 degrees to one another. So those 2 pi bonds have to be 90 degrees to one another when we're looking at the structure. Again, ethine is the simplest of the alkynes. As you can see, it is a pure hydrocarbon, but it is useful for more than just burning. Okay, yes, it's useful in oxyacetylene torches, but to an organic chemist, burning these things seems like a sin. You just get carbon dioxide and water out of that. But what we can do, at least chemically with these things, is actually quite powerful. You can do a lot of chemistry with an alkyne. And so, for example, you can make drugs. All 3 of these molecules are drugs, and if you look at them, you'll see at least 1 carbon triple bond in all of these. Okay? If we remove the carbon-carbon triple bond in these, they no longer have their function. For whatever reason, there needs to be 2 carbons bound together in a linear fashion and for these molecules to work. And the only way to really make that work well is to use a triple bond. Okay? Now, we've got antifungals. So if you have a fungal infection, these things end up in creams. Okay? Most of these things have these triple bonds. This ethinyl estradiol is also known as the pill. Okay? This is an oral contraceptive. Remove the carbon-carbon triple bond, it doesn't work anymore. That becomes a problem. right? So it's very, very important to have your functional groups right where they need to be, or your medicines don't work like they're supposed to, okay? Aromatic hydrocarbons, again, we'll learn more about this in chapter 14, but I just want to introduce here the simplest, well, I shouldn't say the simplest, the most common form of an aromatic hydrocarbon is benzene, C6H6. And it is historically where we started talking about or learning about aromatic compounds, okay? The structure of benzene, believe it or not, was debated for years. There were many, many different structures that were proposed for this molecule, but this is the structure that we have, that we know it to be today, okay? Benzene, a very simple molecule, 6 carbons, 6 hydrogens. It is known as an aromatic compound. It has unusual chemistry and unusual stability that we'll learn more about in chapter 14. Okay? How many units of unsaturation does it have? It has 4. Where do you get 4?
I just like the math.
You did the math. What math did you do?
2n plus 2, and then every 2 is and every 2 that you're missing is 1 unit.
That's right. So where do they come from?
The double bonded carbon.
1, 2, 3,
And then each carbon is bonded to each other.
and then the ring, right? So we get 1 unit of unsaturation from the ring and 3 units of unsaturation from the pi bonds, okay? We typically represent it like that. It's a lot easier. You will also quite frequently see these aromatic molecules represented like this. So if you see it on sapling, don't freak out. The circle means the 3 pi bonds delocalized over the entire system, because we can draw a resonance structure for benzene that move the double bonds around, okay? Cool thing about organic chemistry is we're not limited to just one type of carbon or one type of hydrocarbon in a molecule. We can throw in a lot of different types. If we look at this molecule, alpha prostol, you'll notice that it contains alkanes, things that are just carbon and hydrogen with no pi bonds. We have alkenes, we have alkynes, and we have other functional groups in that molecule that we'll learn about. You put all those functional groups together and connect them in that way, and you have a therapeutic molecule that's used in veterinary medicine. You get rid of the pi bonds, it no longer functions. They've got to be there, okay? Sarah, I think you said positive and negative, opposite charges, right, with dipoles? Does it have to be a complete charge, or can it be a partial charge? It can be a partial charge. Could be a real charge, could be a positive and a negative, but it can also be a partial charge that's due to electronegativity differences, right? So if B is more electronegative than A, we would say that this molecule is polar because B is attracting the electrons in that bond more to itself than to A, right? And so what atom would take on the partial positive charge and which atom would take on the partial negative charge? Okay, so it would be B, right? That's right. So we'd have a partial negative charge on B, a partial positive charge on A. We would say that it has a permanent dipole that goes from A to B. We would draw that with a plus sign here, an arrow going to B, okay? Some examples are HF and water, right? Those both have permanent dipoles, absolutely. But electronegativity differences aren't everything. Carbon tetrachloride, which is shown there, so we have carbon with 4 chlorines on it. I think you all will agree that carbon is less electronegative than chlorine, right? So chlorine is pulling the electrons to itself, and we have a polar bond. Carbon being partially positive, chlorine being partially negative. Carbon tetrachloride is nonpolar. Why? That's right. It's vector math. You'll learn more about that when you get into physics. Okay? But the dipole in one direction is canceled by the dipole in the opposite direction, right? So if Amber was able to actually take a single molecule of carbon tetrachloride and hold it in her hand, no matter how she turned it, it would always look the same. She would only see the negative end of the dipole. She would never be able to see the positive end because that's in the center at the carbon, right? So the outside of it all looks the same no matter how she turns it. So not only do we have to look at electronegativity differences, which you can just get from the periodic table, but you have to know something about structure. Does anybody know anything about carbon tetrachloride? You all are probably a little too young for this one, other than the fact that it's a tetrahedron. This used to be the molecule that you would take your fancy clothes to get dry cleaned. What is dry cleaning? Why do we have dry cleaning? Cleans your comforters?
Yeah.
Okay.
Expensive stuff without like ruining the family.
Yeah, so what if we took a wool jacket, for example, and we put it in water? What happens? It shrinks. It no longer holds its integrity, right? So we dry clean it. Well, carbon tetrachloride is nonpolar. It's not water, right? So they would dip, so to speak, your jacket down into carbon tetrachloride, which is nonpolar. And what do nonpolar things dissolve? Nonpolar stuff. So what am I trying to remove? Where does most of the dirt and grime come from? From our skin, our oils that get into our clothes, right? That's really what you want to get rid of, right? Well, the oils and junk from our normal wear and tear, so to speak, can be dissolved away by carbon tetrachloride. So it was used quite frequently in the dry cleaning industry. It is no longer used in the dry cleaning industry because it causes cancer. Okay? Just a little tiny one. And they realized that people who were in that industry had a huge increase in incidence of, it was either liver or kidney cancer. I can't remember off the top of my head. Okay? If you go to medical school and you end up doing research, this is the way that you give rats cancer. So when I was at Vanderbilt, they actually had somebody that fed these little rats they laced their water with carbon tetrachloride. Because once this stuff hits either their kidney or their liver, I think it's the liver actually, it goes off like a bomb and sets off a whole series of problems that create cancerous situations. Okay, so we no longer dry clean our clothes with carbon tetrachloride for obvious reasons. Okay. What do you think about these? Are they polar or nonpolar? Are all those molecules going to be polar or nonpolar? They're all going to be polar. And which way is the dipole going to go in formaldehyde? Towards the oxygen, right? So if we look at the actual structure, we know that formaldehyde is going to have a trigonal planar structure, and the dipole is going to go from the carbon to the oxygen. Chloroethine. Yep. Dichloromethane. Just to the chlorines? We actually kind of split the difference, right? So we got these two chlorines going out, and the dipole actually is between them because of the three-dimensional structure. How about dimethyl ether? That's right. It's going to go out in that direction, right? So we have this tetrahedral shape at oxygen, counting the electron lone pairs. Okay? Functional groups. You have to know your functional groups early. You're not going to hear me say this too often. You have to memorize these. If making flashcards works for you, do it. I hold you responsible for all the functional groups starting Wednesday. Okay? You've got to know your functional groups. And you just have to commit them to memory. Okay? So a functional group we've already defined a little bit as a atom or a group of atoms that have a characteristical physical or chemical property. All organic molecules, right, will have carbon-carbon and carbon-hydrogen single bonds, And so we largely don't consider that to be a functional group, okay? But on these backbones of carbons and hydrogens, we can actually place heteroatoms. So if you find a heteroatom, that is something that's not carbon or hydrogen, chances are it belongs to a functional group. Pi bonds are good locations for functional groups. And these things, these functional groups let us know how the molecule is going to react. It allows us to know how it's going to be shaped. It allows us to know whether or not it's going to be soluble in water or soluble in something that's nonpolar. Knowing something about the functional groups allows us to do a lot of stuff on paper, at least, okay? So let's look at some molecules that have functional groups. Again, just a pure hydrocarbon, we say that that has no functional group. The only function that there is for a pure hydrocarbon with no functional groups, no pi bonds, is that you can burn it. It's about all you can do with it. It's about all it's useful for, okay? However, if I replace one of these hydrogens on ethane with an OH, I now have a hydroxy group, which is known as an alcohol. So I go from ethane to ethanol. I go from a component of natural gas to beer or wine, whatever your flavor is, okay? So the differences are quite remarkable by just adding an oxygen. It's a gas at room temperature. What is this at room temperature? It's a liquid, right? Very hard to freeze. Not so hard to freeze, actually. Okay? So very different chemical and physical properties. So again, I'm going to give you a list of functional groups. You need to commit these to memory. The alkane, we say, has no functional group. The alkene, it's the double bond. The alkyne, it's the triple bond. The aromatic compound, it's the phenyl group. This benzene ring is also known as a phenyl group when placed into a molecule. So for the hydrocarbons, that's pretty much so it. But that's not the only set of functional groups that we need to know about. You're going to have heteroatoms. So if I put a halogen on, we call these alkyl halides, and the functional group itself is the halogen group or the halo group. Okay? That would be known as an alkyl bromide, for example. Alcohols, the functional group is the hydroxy group. Ethers, the OR group or the alkoxy group is the functional group. Amines, it's the amino group, the nitrogen. Okay? Notice I can have several different types of amines. I can have the nitrogen attached to a single carbon, 2 carbons, or 3 carbons. But in all cases, the nitrogen has what? Lone pair. All amines will have the lone pair. Okay? We'll talk more about amines later on. Thiols. These are known as mercapto functional groups, the SH here. What is this related to in the list? It is related to the alcohol, right? Because oxygen and sulfur are in the same family, right? Are there big differences in their chemistry? There are. If I set out a bottle of alcohol in this room, would you be able to smell it strongly? Nah. If I took a bottle of the thiol and I set it out in the room, would you be able to smell it strongly? Oh, yeah. Oh, yeah. You'd be able to, it'd drive you out of here. Okay? Thiols are what they add to natural gas to give it that characteristic odor. And they literally add just a few milliliters to millions of cubic feet of this stuff to give it the odor that you smell. We have driven people out of the building before using thiols in my lab. They stink. Okay? Sulfides. What do they look like? Well, they are that, but what do they look like? What are they related to? Ethers. That's right. Ethers and sulfides are related, just as alcohols and thiols. are related. Okay? There are a whole series of functional groups that contain what is known as the carbonyl, the carbon doubly bound to oxygen. Okay, there are many, many functional groups that have a carbonyl as a component. You need to know the carbonyl. Okay? It has a pi bond. Okay? And that pi bond is more easily broken than a sigma bond. Pi bonds are weak. Sigma bonds are strong. Can anybody tell me why? What does that mean? That's right. Sigma bonds actually have very strong, good orbital overlap. Right? What about pi bonds? They're side by side, and just the edges of the p orbitals are actually touching to form the bond, right? So they're weaker. Why don't we go ahead and stop there for today? We'll pick this back up on Wednesday and then continue in. So have a good weekend. Have a great Labor Day weekend. Start memorizing your functional groups, even those that we haven't gotten to yet. You have to commit those to memory.